with MOLA technology, but on Earth.
Really had to get those data sets out there, and you had to get a couple people that really bought into it and built on it and convince others that this worked.
As the data from the shuttle laser altimeter began to convince some skeptics, the Goddard team finished the MOLA instrument. Again.
Our MOLA team really came through. It was just really another great experience for many of us, including me. We were able to deliver to the Mars Global Surveyor project, and it got launched.
And we have liftoff of NASA's Mars Global Surveyor as America begins its journey back to the red planet.
6 solids and burning.
And when Mars Global Surveyor started getting closer to Mars, we were going to go into this aerobraking phase. That was an opportunity that we had to go ahead and turn on the lasers and see if we could track the surface.
Somebody big carrying it for me.
And Station 45 was having problems locking up to the 2K data.
What was that? Would you say
1607 or 16?
Can you tell if the MOLA has been turned off?
Copy up, Mike. Tell my query to be started as soon as that query's up.
The native event? That must be the native event.
I'm hungry. I didn't really want those sandwiches.
Look at the laser coming back, Robert.
Rick says about 8
The spacecraft. It's going to be too fast and I got too much data.
Yes.
Look, there's a little tiny terrace. This is the first profile of a crater we've ever seen on the planet.
That is.
Rob, nice laser.
Right here.
We have Mars, finally. 12 years. All right, let's take a look. I don't understand.
Over a decade later, the Goddard team had proof. Planet-scale laser altimetry worked. It could map distant craters and valleys and mountains. It changed the game.
Today, we've ushered in a new era in the remote sensing of Mars.
And this particular data set that we've acquired has in fact enabled us to generate what we consider a very detailed description of the shape of the planet Mars.
This has significant implications for the flow of water early on Mars.
We believe this is one of the youngest features on the planet. We're seeing a planet that is very different from Earth. And it's telling us something about the Earth in an indirect way that says that not everything works in the way that we originally had in mind.
The kind of measurements that we're making now are allowing us to, characterize Mars on time scales of days to years now. And then the next step is to try to go back eons and try to figure out what changed on Mars.
I mean, at that time, we used to brag that Mars was mapped better than the Earth. The accuracy of MOLA was so good, and after a couple of years, the coverage was so good. It was definitely a more accurate map of a planet than any planet.
And this came out of it can't be done in the mid-'80s to a tool that we now accept as the standard.
For those of us that worked on MOLA, it was transformative. It wasn't at a destination or a place that we were as much as a place that we would become.
Following MOLA, in some ways we were in demand to consider whether we could provide a laser altimeter to another mission.
A few missions, actually. It was no longer a question of if LiDAR could work, but where else it could work. But as the opportunities to test the limits of LiDAR arose, so did the challenges ahead. The Goddard team quickly began to see the evolution of LiDAR missions, building on the successes of new frontiers mapped by MOLA.
We've measured the seasonal changes in the Mars ice caps, both the North Pole and the South Pole. We've measured the volumes, we've measured the mass that's involved in that. We now have a density. So now we know the kind of processes that are taking.
Dave Smith invited me to be on the MOLA altimetry science team. And that was because of my experience with using altimetry over land rather than ocean processes.
Zwally was an obvious choice to study the Martian ice caps for MOLA, given his decades of expertise with our own polar regions, studying the ice sheets of Greenland and Antarctica through the 1970s and 80s.
And as we went into the 80s, NASA was It was sort of the beginning of the development of the Earth observations program.
So the Earth Observing System, I think, will be the first effort targeted at looking at the whole Earth system as a system, rather than just the little components that make it up.
Somewhere along then, I teamed up with Jim Abshar.
Jay had been pushing for a long time for a dedicated ice altimetry mission, which turned into ICESat-1.
Designing ICESat-1 marked a major leap in what LiDAR needed to do and how challenging it would be to do it. To measure the changing ice sheets, the LiDAR had to be far more precise, cover the same tracks season to season, and it needed more power and a larger instrument, which meant much more time to build.
We built a simulator for ICESat-1 that allowed us to sort of figure out how precise it could be, how we would process the waveform data coming back, how we would track the surface.
This algorithm was much more complicated than anything I had ever worked on before.
But all this meant essentially for the ICESat mission, you needed a much more advanced version of MOLA.
In Mars, we really didn't know what was there until we got the measurements, so we were doing discovery. On Earth, we have to make quantitative measurements about what's happening.
4, 3, 2, 1. And we have ignition and liftoff of NASA's ICESat and ChipSat spacecraft looking at stars and ice.
But after, we'd worked on GLASS at that point more than a decade, and it had already launched, and usually you think, okay, now we're going to be able to enjoy the data coming down, and what can we see in the data? But there was much more, what is this mystery we're seeing? Why is the laser energy going down? Things were not working the way we expected them to, and there were mysteries, and we weren't expecting, after MOLA in particular, to have mysteries at that point.
One of these unexpected mysteries came down to the wire. Several wires, actually.
What happened on GLASS was the laser diodes had gold bond wires and indium solder. If you bring these two metals together, even though they're not reactive, they do combine to form gold indide.
The gold indide ate away at the wires, leading to added thermal stress, and eventually the failure of the first laser. And the second and third lasers were degrading as well. Tough decisions were ahead.
When these missions operate, there's a lot riding on the missions. You don't want to make any mistakes. You want to optimize things as best you can.
The question was, given that we would have so much lifetime expectancy from the lasers, well, the scientific decision was that the best way to use that was to operate for periods of about a month and do that 3 times a year.
That decision paid off when ICESat showed dramatic change in land ice around Greenland, and it also proved that LiDAR could be used to measure something called sea ice freeboard, a major breakthrough in determining sea ice thickness and an essential science goal for the future of ice measuring satellites.
Even though the ICESat project required much more care and feeding, it really laid the groundwork for all the subsequent missions that Goddard has flown.
Around the same time that ICESat was developed, Goddard was tasked with designing